Hello everyone and welcome back to Intelligent Machines. Today we are going to do a run through of the Jupyter notebook for the implementation of patch code paper that we saw in the previous video. If you haven't seen the video, I request you to go and check out that video, which I'll put somewhere in the I button here. By the end of this video, you will know how to apply practically the anomaly detection method, which is proposed by Amazon's scientist and has the state-of-the-art result on the most popular anomaly detection dataset. So let's roll the intro. And to start with, first we'll import the necessary libraries that we have been doing for so long. Then we define our transforms, which is nothing but just resizing our image into 224 cross 224 just for memory constraints, and then bringing them to a Pytorch tensor. That's it. And now comes the important part, that loading the ResNet model. So we are going to extract the intermediate layer that I told about in the last video. If you do not know how to extract or how to use this forward hooks, I already have a video on it. I request you to check it out in the I button. After we extract the intermediate layer, then we aggregate them using adaptive average pooling, so that they have the same height and width. Then we concatenate them along the channel direction, as you can see here. First we do the aggregation, then we concatenate them. That's it. So what does this patch contain? This patch contain total 784 patches extracted from the same image. However, each patch has a 1536 number of feature, which are basically the channel dimension. Alright, so what I did here is I extracted one image from here and I printed out how many features I have there. So I have total 784 patches and each patch having 1536. And our next goal is to create a memory bank. So how we'll create a memory bank? We'll just iterate through our training data, which only consists of good images, and we'll extract patch of each image and just concatenate them. That's it. That's it. All is happening here. Then this is the additional tips that I shared in the previous video, that we cannot use all the patches that we have in our memory bank, because during the inference we have to calculate distance with respect to each and every patch in our memory bank, and it will be very computationally expensive. So we just randomly select 10% of the patches in the paper, in the patch core paper of the implementation. They provide a core set sampling method, but it doesn't have a very big difference where if you use core set or if you use random sampling, in my opinion. But you can also try the core set sampling. So yeah, this is just a random sampling of 10% of the data of the memory bank, so we don't have to do a lot of distance calculation. And yeah, that's it. Our training is done. In this method, one biggest advantage is it does not require any training. So this is a very big advantage compared to the previous autoencoder method that we saw, which needs a long amount of training, at least for 2 to 3 hours of training minimum required. But in this case, there is no training required. So that is a big plus for it. Next, directly we can go ahead and test it. For now, we'll see how it performs on only the good images. So we iterate through all the folder of the good images. We extract the feature here. Then we calculate its pairwise distance with respect to the patches in the memory bank. This feature contain patch corresponding to each image of the good class. Then we just calculate the distance score, and the maximum of the distance score is our anomaly score for the image. And if we reshape this distance score into 28 cross 28, that will become our heat map. So whichever part will have higher value, that will signify, okay, there is a fault in this region. Alright, after we calculate the anomaly score for all the image in our test dataset, then we plot the histogram corresponding to that, and we saw that most of the anomaly score from the normal image lies behind 9.5. So we can say, for now, let's take 9.5 as our anomaly threshold. If the anomaly score is higher than 9.5, we say, okay, this belongs to an anomaly case for now. So now it's time to go ahead and check on the not okay images. there is different type of faults available, and we did the same that we did for the previous case. And I'll just run this one. Alright, so this is run, and we have secured the y score, which is the anomaly score for the test data set, and we plot it only for the not okay class. Y equal to 1 represents the not okay class. There you see that most of them lies ahead of our threshold that we just set. That means our model performs pretty good. And the next thing is the anomaly localization. For that we get this distance score by doing the pairwise distance. Then we reshape that distance score into 28 cross 28, which we call the segmentation map, for anomaly segmentation map. And we can bilinearly interpolate them to bring back to the size of our image. For the overlaying, we overlay the heat map on our image to especially see where there is the fault, just for aesthetic purposes. And we see something like this for the image belonging to 0.0. So which one? This one. Yeah, this is the actual image, and this is the anomaly localization graph for that. So you see it's pretty accurate. And finally, some metrics to evaluate. For this we are using ROC curve, and we see that we get a ROC curve of 0.97 area under the ROC curve. If it's 1, then of course it's great. For the previous case where we did anomaly detection using autoencoder and deep features, we got 0.98 or something. But in that case, we need to spend a lot of computation and time on training as well. But here there is no training needed, so that's a good thing. We can run this code to see in real time how is our performance. There's a fault here, it detects. It will detect whenever there is a fault with a very high accuracy. So yeah, that was all about this video. I hope you enjoyed it. If you want to book a personal one-to-one call, don't forget to check out my link given in the description for top meet. See you. Bye bye.